Okay, so let's start. Uh, so from today, uh, we shall be continuing our discussion on four vectors. I already introduced it in the last class, and I have my pen tab with me. So today is the first day I will try to deliver my lecture with this pen tab. So let us see how it goes. So let me first go to the no, not this one. Present now. Can you see the whiteboard? Can you see the white?
Yes,
Okay,
yes, sir.
okay, okay,
Yes, sir.
okay, fine. So I have already told you about four velocity and four momentum in the last class, and as I told you that if you work in the framework of special relativity using four vector notation has several advantage, and I have already given you a couple of example like few kinematic problems like proton antiproton pair production, and there were some other examples which I had not time to discuss in the last class, but I hope you can understand those examples which I have given in the notes in the previous days class, previous this lecture notes. So if you have any difficulty you can ask me. So I am not going to repeat what I have already discussed in the last class. Let us discuss a couple of other examples and then move forward. So as I told you that four vectors. So, okay, let me write down. Uh, okay. So define four vectors in the way that four vectors. So four vectors are defined to be vectors which are defined within the four-dimensional space-time. And as I told you that the four-dimensional space-time is not a Euclidean, it is hyperbolic in nature. So it is not just adding another component to a three vector to make it a four vector. So if you just randomly pick up four numbers and label it as a four vector, that will be wrong. So and the hyperbolic nature of space-time is a consequence of the upper limit in the speed of light in the universe. Since there is a speed limit that automatically makes the geometry of space-time hyperbolic, and once we are in the hyperbolic space-time geometry, uh, the four vectors that we define, for example the space-time four vector, or the uh, which we denoted as x mu, this is space-time four vector, right? So x mu was what? The time component ct, comma the three spatial component ct and r. Pardon me for the handwriting because I am not still very much acquainted with this device, so I'm just using it for the first time. So if you have any difficulty in reading, then of course you can let me know. So x mu is the space-time four vector, and we know how it transform if we go from one inertial frame to other. So of course, we can calculate the different component of x mu in the prime frame. So what are those transformation? If you remember, x0 prime, that is equal to gamma v. Remember, I didn't use this subscript because gamma is a Lorentz factor, which can be any Lorentz factor associated with any velocity. So here I am talking about the velocity of the boost, Lorentz boost, v. Gamma v, this is x0 unfined frame, minus beta is v by c, of course, and then you have x1, that is space component, the first. And of course I am talking about a particular transformation where the prime frame is moving along the x-axis, right, with velocity v, that we have already discussed. And then the first spatial component x1 prime will be, there is a nice symmetry, so don't need to remember it separately. If you know one, you can write the other, x1 minus beta x0. And of course, since there are no motion along y or z axis, this two remains unchanged, x2 prime equal to x2 and x3 prime equal to x3. Now this, okay, just a minute. Can you see the slide now? Hello.
Yes, sir. Yes,
Okay.
sir.
Okay. So these are the transformation which we call Lorentz transformation. It's not new to us. So we define the four vectors in such a way that have to obey Lorentz transformation, because these four vectors live in four-dimensional space-time, which is hyperbolic, and that is the Lorentz transformation. And one can have different four vectors, like the two which we have discussed in the last class, like four velocity and four momentum. Of course, there are many. And one of the most important thing that I have already told you, that the norm of the four vector of the, or the length of the four vector, that doesn't change if you go from one frame to other, inertial frame, of course. And I also told you that these Lorentz boost or transformations are nothing but rotation, simple rotation. Like we rotate our coordinate system in Euclidean geometry, we get another set of coordinate for a vector, but the length of the vector doesn't change. It is very similar, but of course the geometry is different, right? So any if I take any four vectors, say example x mu, which we call, of course, what we label it, we label this as the space-time interval, right? C square t square minus r square, right? We label this as a interval, and this is invariant, low range invariant. So this doesn't change, right? Low range invariant. Of course, I can have different set of four vector for which this quantity can be positive, negative, or zero, and depending on the value of this quantity, one can label the different four vector space like four vector, time like four vector, or light like four vector. I also told you that if you take any two four vector, like say I have a four vector a mu and another four vector say b mu, so I take a scalar product between them, this will be also Lorentz invariant, right? This will be also invariant, right? You don't need to worry about the product. So the advantage is that once you know the two four vector in any one frame, you can go to any other frame and you can be assured that the product remains invariant. And this actually provides us lots of advantage, which we are using right now for the problems that I discussed. And the advantage is basically then you can choose your I mean your particular frame of reference where the calculations are easier. For example, if I give you one particle which has certain energy or momentum, and it collides with something and produces something, then it is always easier to go to the rest frame of the particle or the center of momentum frame of the set of particle, where only the time components are there, and your calculation becomes a lot of easy. So this is space-time four vector. Similarly, you can of course define other four vectors which I've already defined. Let me add another page. For example, let me again rewrite the four velocity. I just write the expression, nothing more than the expression, because other things we have already discussed. So four velocity we define as u mu, which is dx mu d tau. If you remember, it is the derivative of the space-time interval with respect to the proper time, right? With respect to proper time. And this quantity comes out to be again that transform like a space-time four vector. Why? Because this quantity is Lorentz invariant, so it just transforms like the four vector, space-time four vector. And we know that if I calculate this, I know the relationship between time and proper time. So we can write this as gamma. What should I write here? Gamma v or u? Gamma u, right? Because u is the velocity of the particle. Here we are trying to write the four velocity of a particle, right? I am not talking about a particular frame of reference. It is the velocity of a particle in a given frame. Okay, so gamma u is the Lorentz factor associated with the velocity, three velocity of the particle, gamma u, right? And gamma u, and then the time component is gamma u c, and the spatial components are as usual ux, uy, and uz. So I'm writing in a short notation, u is the three vector. So this is four velocity. right? The four components of, again, they transform, just following Lorentz transformation, so there is no need to write u0 prime equal to gamma v. Now this time you have to write gamma v because you are transforming between two frames, so don't get confused between gamma u and gamma v. If I want to transform the components between two different frames, then I have to use gamma v, not gamma u. Gamma u is the Lorentz factor of the particle in a given frame where the velocity is u. In another frame, velocity could be something else, so which we have already discussed in the last class, how the different components of velocity transform between two inertial frames. And I already showed you that the transformation is much easier in the four-dimensional space-time, of course, because they obey Lorentz transformation, which is symmetrical, easy to follow. If you go to three dimension, basically you are transforming both in space and time, and that's why they look ugly and complicated. So dealing with objects which are actually four-dimensional in four dimension, it definitely going to be easier. And then I talked about four momentum. So I'm not writing the transformation because they are very similar. So four momentum, I told you that energy and momentum, which we dealt separately earlier, are actually a component of a four vector, which we called four momentum. So let us label that as p mu. The p mu is the four momentum. The time component of the four momentum is nothing but energy of the particle, that means rest mass energy plus kinetic energy divided by c, and then usual three momentum, which you call px, py, pz, right? So these are nothing but the four components of a single four vector. So you don't need to think energy and momentum separately. They are nothing but the components of a single vector, four momentum. So it is easier to think energy momentum as a unified quantity, that is four momentum, and that is what we have applied in a couple of problems in the last class. Let me discuss one particular example which I think all of you are familiar with, because in BSc, probably first year or second year, no, I think it would be second year or third year, because you learned quantum mechanics probably in the last semester or maybe fifth semester, I don't know. So yes, so when you learn quantum mechanics, you learn about different kind of effects, like photoelectric effect, Compton effect, which actually provides you some idea about the this wave particle duality. The particle can a photon can be a wave as well as a particle, and one of the example of the particle nature of photon is the Compton effect, where an X-ray photon or a gamma photon individually collides with an electron, and when it scatters off, its wavelength increases, right? So it can, so that's known as Compton effect. Of course, it happens in X-ray or gamma ray. Why not in optical? That is another question, which I'm not going to discuss about the physics of Compton effect. There are several different aspects of Compton effect. Here I will just describe the formula of Compton shift using four vector notation, and I will show you that it's much easier. You don't need to think energy conservation, momentum conservation, and so on separately. So let us discuss about the Compton effect. So I'm going to discuss about, say, Compton effect. So what is Compton effect? All of you know what Compton effect is. So I'm just briefly Compton effect. It is the scattering of a photon. So you have some photon coming from, say, this direction, right? And you have an electron here sitting here, say electron, whose rest mass is, say, m0 or me, whatever you like to want to write. And suppose the frequency of the incoming photon is nu. Okay. And so let us, since we are going to deal with the four momentum of these particles like photons and electrons, let us label the four momentum of the photon as, say, p nu, and of course it's a four momentum, so I write mu here. Okay. And similarly, let us denote the four momentum of the electron as, say, p mu of the electron. So we have to use some kind of notation, right? And suppose the photon is going in this direction, electron is at rest somewhere in this frame, lab frame. So suppose this is x direction, you can, this is x direction. Of course, you can x, this is y, and perpendicular to this plane is z direction. And this is before the collision. This is a picture before the collision. So let us write, this is before the collision. Of course, we can write the picture of this outcome of this collision So what happens after this collision is that the photon no longer travels in the same direction. Suppose this is x direction, right, which you have denoted here. This is x direction. So the photon scatters off some other direction. Let us call this angle to be theta nu, and this the frequency of the photon will not be same as the original. Let's call this nu prime, and the electron gets scattered into some other direction. Could be any direction depending on the collision. So this, let's call this electron. Now the rest mass is m0, and now the electron is moving with some velocity, so the energy will be definitely different, right? So when you write 4 momentum, you should be careful which are the known quantities, which are the unknown quantities, and suppose this angle is theta electron, right? So this is the picture after the collision, right? This is after the collision. So what we are going to apply is basically the 4 momentum conservation, which is pretty straightforward, right? We have the 4 momentum of the photon and the electron before the collision. Let us label the 4 momentum of the photon of the collision after the collision as p mu prime. I'm writing a prime. I'm not writing a new prime again because that would be confusing. Just remember, nu is for photon. Okay, this prime is after the collision, and unprimed is basically before the collision. Okay, that you can write down using language. Okay, that's up to you. And suppose this is the 4 momentum of the electron after the collision. Let us call it prime. So here, see, this prime and unprime, don't just assume that prime means it's a Lorentz transformation, and I am applying Lorentz transformation to go to another inertial frame. This is a kind of just labeling. You can also write P is scattered or whatever. So I have just chosen a particular notation, and here it's electron. And in 4 vector notation, what is the principle of 4 momentum conservation? So the momentum of the particle, that is the photon, say P mu of the photon, if I add that to the 4 momentum of the electron, that should be same as the 4 momentum of the photon after the collision on the electrons. The same systems are, I mean, the before and after, we have just a photon and an electron, nothing else, no new particle here. As I have given you a couple of examples where new particles may appear, but here there are no new particles. And this is electron. Now, I told you that the norm of the 4 vector remains invariant. So you may wonder that simply I have to take a scalar product of the left hand side with itself and the right hand side with itself. But wait, but if you blindly do this, sometime you may land into problem. So you should actually look at the quantities on the both side, right? You see P mu nu, I know what is the frequency, suppose it's given to you. You know the mass of the electron, right? So since the electron is at rest, you already know the 4 momentum, because it is the rest mass energy divided by c, that is m0c, right? The time component, and there are no special component because the electron is at rest in this frame. And the photon, for the photon, I already told you that it is interesting that you can write down the 4 momentum of a photon, but not the 4 velocity, because photons have no rest frame. So that's why you cannot write down the 4 velocity of a photon, but the 4 momentum is possible, because momentum is 4 momentum is energy and momentum, and photons have both. Photons have energy, photons have momentum, so you can write down the 4 momentum. So once you know the frequency, you know the energy, you know the momentum. What is the momentum of a photon? It is E by C, right? So depending on which direction it is traveling, you can write down the 4 momentum of a photon. On the right hand side, if you look carefully, what are the things? This quantity is the 4 momentum of the scattered photon, for which you again, if you know the frequency, then you can write down the 4 momentum of the scattered photon. And what about the electron? You see, electron rest mass is known, but here you do not know what is the velocity of that electron which is scattered, right? And also you have to know several things like the 2 angles, theta nu and theta e. So more unknown you involve into the equation, the things become more complicated, right? So it is e.g., if I see, as I told you, it doesn't matter whether you are working on the center of momentum frame or the rest frame of the particle or the lab frame. Whichever frame you go, the norm of the 4 vector, the length of the 4 vector doesn't change. So it will be my choice. right? I will calculate the quantities in the choice of in the frame where I find it easier to calculate. So যেখানে সহজে ক্যালকুলেট করা যাবে সেখানেই ক্যালকুলেট করবো আমরা। তাহলে দেখো, so now, so you see this quantity, if I keep this quantity on one side, that is the electron, যদি আমি এভাবে লিখি, কোনো নেসেসিটি নেই কিন্তু, you can write square the quantities on both sides if you like, but only thing the equation will be, calculation will be more complicated. So here what I am doing, I am doing it simple trick. It's not a trick really, it's because it is a choice of rewriting things. So I am writing p mu prime electron equal to p mu photon plus p mu electron minus, because they are vectors, p mu photon. If I write this way, the advantage is that when I take the norm on both sides, you see, if I take the norm on the left hand side, you tell me what is the quantity on the left hand side. It is just the 4 momentum of the scattered electron, and you know that the scattered electron, right, whether it has a velocity or not, what is the length of the 4 momentum of any electron, whether it's rest or it is moving with some velocity. If I keep this quantity on the right hand side, when I square them or when I take the norm, there will be a cross term involving both the photon, 4 momentum of the photon and electron. If I do not know what is the angle of scattering of the electron or what is the velocity of the electron, I will be in trouble, because how do I write? I know one, and then I can of course use some notation, but those are unknown to me. I do not know what is the velocity of the scattered electron, what is the angle theta e. So we want to keep the number of unknown to minimum. So if I write the equation, rewrite the equation in this fashion, the problem will be a bit easier. You see, if I now take the norm on both sides, what do I write? I write p mu prime, p mu of course prime electron, right, is equal to, you see, I am just taking the norm on both sides. So this will be p mu nu plus p mu electron plus this time p mu prime. Again I tell you that prime is not the quantities in the some boosted frame. These are just levels I am using. Of course you can choose a different level if you like. Nu, because the photon again, and then you have a plus, because this and this are plus sign.
লাস্টের টার্মটাতে মাইনাস হবে না?
না, a plus b minus c তার স্কয়ার করলে কি হয়? 2 p mu nu. I am writing them separately, these quantities, because they are not p mu and electron. This will be plus, and then this last two quantities will be negative. আচ্ছা আগে লিখে নি, তারপর I'm going to explain all the terms. P mu nu, right, and p mu prime nu, just cross term গুলো লিখছি। একটা মাইনাস আছে, সুতরাং প্লাস মাইনাসে মাইনাস হবে, প্লাস মাইনাসে মাইনাস হবে, প্লাসে প্লাসে প্লাস হবে। ফার্স্টটা প্লাস আছে, তারপর মাইনাস লিখছি। তারপরে কি হচ্ছে, মাইনাস, আরেকটা হবে মাইনাস অফ 2 p mu electron and p mu, এটা প্রাইম, একটা প্রাইম একটা আনপ্রাইম, এটা হচ্ছে ফোটন। দেখে নাও, if you have any doubts you can clarify. So I have written all the terms, right, in the 4 vector notation. So right hand side, left hand side is this, right hand side I have 3 terms. If you square that, basically you have 3 cross terms and 3 individual terms, right? Now you see, I told you that it is your choice which frame is more convenient to you, just choose it. So let us first write down the 4 momentums. Unless we write down the 4 momentums, it will not be easier to decide where to calculate things, right? So is there any question up to this? If you have, please ask. Okay, So let us now move to the next page. That little space here, new page after. Okay, so I'm writing the individual four momentum. So what is the four momentum of the photon? For example, if I ask you what is the four momentum of the photon before the collision, so let us. So I'm not writing the words. Okay, p mu. If I want to write the four momentum of the photon before collision, you tell me what is the first component. It is energy divided by c, right? So energy is known to you. The energy of a photon is h times the frequency. H is the Planck's constant, so E by c. And the photon which we considered in the lab frame was moving in the x direction, right? So the momentum of the photon in this frame is along x direction. So I write p, and there is no component of momentum along y or z direction, right? 0 0, right? Here if I want to write down explicitly what is v, you know the momentum of a photon is E by c, right? So E by c. I don't need to put a vector here because it is already implied that it's x component, right? I don't need to put a vector because when I couple them together, then I write p vector. It's meaningless, right? Sorry for that. So right, so E by c, and the x component is again p equal to E by c. So I write E by c. There is no y component 0, z component 0. So this is the four momentum of the photon before collision. Let me write down the same four momentum of the photon after the collision. So what is that? So let me write that p mu. I labeled it as prime. Yeah, so I write for prime here, and it is for the photon. Now this time, see, since I showed you that the photon scatters off at an angle theta nu from the x-axis, so I have to write the four momentum accordingly. So what are the components of the four momentum in this case then? You see the frequency of the photon. You can write down E to be explicitly h nu by c, h nu by c if you like, right? So I have not written it. You can write it. And in this time, you see the energy is different. E prime, that is h nu prime by c. Okay, so this time it is E, not E prime by c, which is h nu prime. So time component is different than what it was before the collision. And what is the x component of momentum of the scattered photon? Because it has now x component and y component both, because it is not moving along the x direction. It scatters off along some direction theta nu. So that's why, say, let us call it p prime. I write this as a cos theta nu. This is the x component, and then we have a p prime sine theta nu, and of course there are no z component, that is 0, right? And since we know all these, this E prime is nothing but h nu prime by c. Of course I can write this to be, if I want, I can write this to be h nu by c. In place of E, I can write h nu by c, right? H nu. So h nu prime by c, and this one is h nu prime by c cos of theta nu. This is h nu prime by c sine of theta nu, and this is 0. Now we want to write down the pole momentum of the electron before the collision, right? P mu electron. This is quite straightforward because the electron is not moving, it is at rest in that lab frame. So I have simply E by c. There are no special component, all the special components are 0, and time component is E by c. It is at rest, so it is the rest mass energy m0 c square divided by c. That will be m0 times c, right? Comma 0 0 0. This is the four momentum of the electron before the collision. Now if I'm interested in writing the four momentum after the collision, you see there are several unknown because I do not know the velocity. So in that case, I have to write down as m0 c plus some velocity term, half m0 is u square divided by c. And also, since I do not know exactly what is the momentum or the speed of the electron after the scattering, so I'm not able to write what are the px and py components, right? So in order to avoid that, I had rewritten the this four momentum conservation in that way, which I already told you, that I took this four momentum of the electron on the left hand side, and kept all the three other on one side. Why? Because I don't have to deal with the problem of knowing that. So that's why I'm not writing it here. I don't need to know that. If I would have continued in the same fashion, like squaring both sides with the quantities which are on the left hand side and the right hand side, then I had to know each and everything, all the all the four momentums, right? That is the four momentum of the photons before collision, after collision, and the four momentum of electrons before collision, after collision. In this case, I don't need to know the four momentum of the electron after collision. That's the advantage that it offers. Okay, now I am since I have already it is not here, so I'm rewriting the equation once again. If you remember, this was p mu of prime, of course, prime of the electron. This was equal to p mu of photon plus p mu of electron plus p mu prime of the photon plus twice p mu photon electron mixture, p mu of electron, and then photon mixture twice mu minus of twice p mu of a photon and p mu prime of the photon, I mean scattered photon, and then I had minus of 2 p mu of electron and p mu prime of photon, p mu prime scattered photon of. Now you see, if you look at the individual terms, you tell me, if I take this norm of the four momentum of the electron, it doesn't matter which frame I go, whether it's a moving frame, whether it's a frame at rest, it remains invariant. You see, so it's most straightforward to calculate in the rest frame. So what will be the left hand side? Although it's a prime quantity, but I'm confident that p mu prime will be equal to p mu. So I calculate it from this expression p mu, which is nothing but m0 square c square, right? So left hand side is m0 square c square. Although I'm calculating it in the rest frame of the electron, right? But that is bound to be equal to the in the moving frame as well, right? So that's why that's the advantage, right? And I don't mix it up with other terms. And then on the right hand side, what are the things you see? If I write down the cross this one, p mu of photon. What is p mu of photon? What is p mu of photon?
m0 square c square.
কি হবে তাহলে? ফোটনের জন্য বলছি, ফোটনের জন্য কি m0, ফোটনের মাস কি m0?
h nu by c
h nu by c না, ভালো করে দেখো। ওকে, আমি আবার বলছি, p mu 0 হবে। দেখো না এক্সপ্রেশন, দেখো কি লেখা আছে, e by c বা h nu by c h nu। তাহলে আমি স্কোয়ার করি, তাহলে h nu c by c স্কোয়ার, তাই তো, মাইনাস h nu by c স্কোয়ার কত হবে? 0 হবে, রাইট? সো ফোটনের, এটা মনে রাখবে, ফোটনের ফোর মোমেন্টামের যে লেংথ নর্ম, সেটা সবসময় 0 হয়, যে কোনো ফ্রেমেই যাও না কেন, রাইট? যে কোনো ফ্রেমে যাও, ফোটনের ফোর মোমেন্টাম যে নর্ম সেটা সবসময় 0 হবে। সো 0, রাইট? And then we have electron, but in the rest frame. But doesn't matter whether rest frame or moving frame যাই হোক না কেন, আমি জানি তো p mu of electron সবসময় এটাই হবে, রাইট? এটাই হবে। আমি রেস্ট ফ্রেমে ক্যালকুলেট করে নিয়েছি, এখন তুমি যে কোনো ফ্রেমে নিয়ে যাও, এটাই হবে, জানি। সেটাই অ্যাডভান্টেজ স্কোয়ার করে নেওয়ার, রাইট? প্লাস আবার দেখো, এটা স্ক্যাটার ফোটনের জন্য কি যায় আসে, স্ক্যাটার ফোটনের হলেও আমি জানি যে তুমি এখানে করে দেখতে পারো, cos স্কোয়ার থিটা sin স্কোয়ার থিটা যোগ করলে 1 হয়ে যাবে। আবার সেটা h স্কোয়ার নিউ প্রাইম স্কোয়ার বাই c স্কোয়ার মাইনাস h স্কোয়ার নিউ প্রাইম স্কোয়ার বাই c স্কোয়ার ইনটু ব্র্যাকেটে থাকবে cos স্কোয়ার থিটা প্লাস sin স্কোয়ার থিটা, which is 1. So if you take the p mu prime of photon in another frame, it is bound to be 0, right? So it is 0 মানে ফিক্স হয়ে গেছে একবার 0, এটা যেখানে যাও সবসময় 0 হবে, রাইট? প্লাস এই কোয়ান্টিটি গুলো কি হবে? এই যে প্লাস ক্রস টার্ম গুলো রয়েছে, ক্রস টার্ম গুলো লেখা যাক কেয়ারফুলি। একটাতে রয়েছে photon electron. You see the p mu photon. What is p mu photon? It is not for the scattered one, it is the original one, and this is the for the electron, right? So p mu photon, p mu electron. For the electron, I do not have any special part, so I don't have to bother about special part at all when I'm multiplying this vector with some other four vectors, because that is going to be 0, right? Special parts are going to be 0. Just look at the time component, m0c, ওখানে কি আছে? h nu by c, right? এখানে আছে h nu by c. You can little bit rearrange these things if you like. এটাকে সাজিয়ে নেওয়া যাক। এখানে এগুলো লিখছি না, জায়গা নেই, জায়গাটা কম পড়ে যাবে। What happened? সো এখানে এগুলো থাকবে, বাদ বাকি টার্মগুলো ওই টু টুয়াইস দিয়ে আমি লিখছি না এখানে। কোথায় চলে যাচ্ছে এটা? হ্যাঁ, টু ব্র্যাকেট দিয়ে যা যা আছে এ থাকবে। এখন দেখো এখানে এটা কেটে যাবে, m0 স্কোয়ার c স্কোয়ার, এটা এদিকে বাঁ দিকে আছে, ডান দিকে আছে, দুদিকে কেটে যাবে, থাকবে না এটা, তাই তো? তাহলে বাদ বাকি পড়ে থাকবে শুধুমাত্র ক্রস টার্মগুলো। উই হ্যাভ অনলি 3 cross terms. We are left with these 3 cross terms, right? And you can rearrange them if you like, because that will be easier to then take the product and simplify the terms. So what I am doing here, I am writing this electron and this photon terms on one side and the photon terms on another side. So let us go to the next page. Just follow the calculation here from here. Option pages, new page after. Okay. So what I'm going to do, I'm going to take the scalar product of the so I'm going to write p mu nu and p mu prime. So okay, let me write this, otherwise it will be confusing. So what I'm writing here, twice p mu nu, ওটা মাইনাস ছিল ওদিকে, এদিকে চলে এলে প্লাস হয়ে যাবে, p mu, এটা নিউ ফোটন, এটা বাঁ দিকে লিখলাম, রাইট? আর এদিকে থাকলো ইকুয়াল টু, টু গুলো ফেলে দেওয়া যায় কারণ সবকটা টার্মের সঙ্গে টু রয়েছে, পি মিউ, রাইট? পি মিউ অফ কি ছিল যেন, একটা হচ্ছে ফোটন, তাহলে একটা পি মিউ এটা প্রাইম হবে, ভুল লিখছি, এটা প্রাইম হবে, একটা হবে ফোটন, ওদিকে ছিল ফোটন ইলেকট্রন, তাই তো ছিল, হ্যাঁ, ইকুয়াল টুয়াইস মিউ ফোটন and twice this will be p mu, of course this is not prime, this is electron, right? This is electron, এটা ওইদিকে প্লাস আর একটা মাইনাস হবে, ইলেকট্রন ফোটন মাইনাস twice p mu electron and p mu prime photon, right? Now look at the left hand side. If I take the scalar product between the 4 momentum of the original photon and the scattered photon, what are the different components? If you remember, for the original photons we have only x component, that is h nu by c, comma h nu by c, comma 0, comma 0. For the scattered photon, h nu prime by c, comma h nu prime by c cos theta nu, comma h nu prime by c sin theta nu, comma 0. There are no z components. So if I take a scalar product time, so h nu by c of the original photon multiplied, this is time component, h nu prime by c, and then I'm multiplying the components, the special components, right? So h nu prime by c, wait, whether I have written it correctly, nu photon photon minus electron photon, ঠিকই আছে, okay, minus h nu by c, h nu prime by c into cos of theta nu equal to h nu, টুটা বাদ দিয়ে দেয়, টুগুলো থাকার কোনো মানে হয় না, টুগুলো থাকবে না দুটো সাইড থেকেই, রাইট? অ্যান্ড দিস সাইড, এটা যদি নেই তাহলে ফোটনের যেহেতু কোনো স্পেশাল মোমেন্টাম নেই, 0, ইট ইজ ইন দ্য রেস্ট ফ্রেম, সো আই জাস্ট হ্যাভ ফোটনের জন্য h nu by c আর ওর জন্য হচ্ছে m0 c ইলেকট্রনের জন্য, রাইট? অ্যান্ড মাইনাস কি আছে, মাইনাস এখানে কি আছে, ইলেকট্রন অ্যান্ড স্ক্যাটার্ড ফোটন, রাইট? ইলেকট্রনের জন্য আবার যেটা বললাম স্পেশাল পার্টটা তো নেই, শুধুমাত্র টাইম পার্টটা রয়েছে, তাহলে আবার লিখবো, কি লিখবো, m0 c, and what is the time part of the scattered photon, h nu prime by c, h nu prime by c, there is no cos theta sin theta, that is in the special part, right? This is what we have after the simplification. And now if I write nu in terms of lambda, yeah, okay, actually you can actually drop the or you don't need to drop actually, because nu by c you can write h into h, that is h square. I can write h square divided by lambda into lambda prime, c equal to nu lambda. So I'm writing nu by c, okay, minus in terms of lambda cos theta nu equal to, this will be, I have h m0 c, I'm taking them common, h m0 c, and we have 1 by lambda minus 1 by lambda prime. Just I'm rewriting nu and c in terms of lambda, right? Yeah, correct. And then here we have c square, right? Here we have c, so that I have already cancelled that. No, I have not cancelled. I have just rewritten in this in terms of lambda, right? I could have cancelled that and written that in terms of nu, and then I had to rewrite them again in terms of lambda. That's why I just avoided that. So this will be h টা কেটে যাবে, দুদিকে h আছে, তাহলে h by lambda times lambda prime, this lambda into lambda prime into 1 minus cos of theta nu will be simply m0c into lambda prime minus lambda divided by lambda lambda prime. এটা both side থেকে দিতে পারো, lambda lambda prime এখানে আছে, এখানেও আছে, right? Right. And you see what is lambda prime minus lambda? This is the change in wavelength of the photon. Scattered photon has a larger wavelength than the original photon because it loses energy during the collision. So lambda prime minus lambda, let us call that delta lambda. Okay, if I write delta lambda is equal to, it will be h by m0c. This is the well-known Compton shift formula which you have learned in your other course, like quantum mechanics. H by m0c into 1 minus cos theta nu, right? This is the formula for Compton shift, the change in wavelength of the scattered photon. So this is one example, and this shift in the wavelength of the scattered photon depends only on the angle of scattering. That is the interesting part of Compton effect. It doesn't depend on the wavelength of the incident radiation, right? It just depends on the angle, right? Change the angle, there will be change in the wavelength, right? And you see we have arrived at this formula using 4 vector notation. So it is clear that you can apply this 4 vector formalism to any problem which involves collision or new particle creation. So these techniques are very useful in particle physics, okay, right? The particle physicists use these techniques very often in their calculations of particle collision and particle creation or annihilation. So one can discuss many such problem, and there is no need to do that. I just wanted to show you the advantage of 4 vector formalism. One more thing, see, in this particular problem there were no Lorentz transforms involved, right? I have not applied any Lorentz transforms. I have just applied some 4 vector conservation principle to this problem, but there could be some problem where you may need to consider the transformation of the 4 vectors, right? So we should be careful depending on the question you have to. So I will give one such example where you may need to apply Lorentz transformation as well. So let me just give one more example, then I will move into some other 4 vector, not this one. After, okay. So now I will give you another example and show you how the application of a Lorentz boost change the perspective of the physical phenomena which is occurring in different frames. We already know about length contraction, time dilation, or the other things, but here we are particularly discussing about the collision between different particles or creation of particles from a particle and so on. So here I am going to discuss about a particular physical phenomena where a pion is decaying into 2 photons in its own rest frame. Okay, so first I will discuss the decay of the pion in its own rest frame. So let us choose our axis, and first, okay, let me just draw so I can choose. It's not looking good. Okay, just a minute. Okay, suppose I choose this line to be my z axis. I can of course choose this to be x axis as well, but again I'm just describing this way. You can choose any axis to be x or z. Okay, now suppose there is a pion at the origin of this coordinate system. It's a pion here which disintegrates into 2 photon, right? So and that photon, say this is a 1 photon. And why this has to be the case? It has to be some other direction. And now this angle could be any angle, right? This could be any angle. Let us call this to be the center of momentum frame. It will be easier then. This is, let us call this theta cm in the center of momentum frame. This could be any angle, right? It could be any angle, 30 degree, 15 degree, whatever. And we have two photons coming out of this single pion. And why this angle has to be also theta cm, that has to be discussed first. These two angles has to be same. And this pion decaying into two photons has to be studied from two different inertial frames. Okay, I'm giving you one assignment. Probably I don't know whether you have solved it earlier or not. You can actually ask the question why pair production in vacuum is not feasible, right? Why a photon doesn't disintegrate into an electron and a positron spontaneously, right? So that question can be answered from this 4-vector perspective, which you can try. It's an easy problem. Okay, so let us discuss this. So that this has nothing to do with that problem. So we have a pi meson here, pi 0, decaying into two photons. And if I ask you what is the 4 momentum of this pi meson, say p mu pi, that is known to you because it is in rest. So I simply write m pi is the mass of the pi meson, c comma 0. Okay, I'm not writing x, y, z to it. There's 0. All special components are 0. Okay, shorthand notation like this one. Now if I ask you what are the 4 momentum of the first photon, say let us call it this one as a nu 1 and this one as a nu 2, right? 2 photons, right? If I ask you what are the 4 momentum of these 2 photons, right? So what is p mu of this photon? If I ask you, simply energy, that is h nu e nu by c, comma, what will be the spatial part? Similarly here, if I ask you what is, say, p mu of, say, again it is another photon, so I should write nu 1 here actually, nu 1. Okay, then I should also write nu 1. Okay, I'm not writing nu 1, nu 2 all the time because they are eventually going to be the same. So here you can write e nu 1 and so on. P mu nu 2 second photon is equal to the energy divided by c is the time, that is e nu. Of course, you can write nu 2 if you like, e nu 1 nu c. Okay, nu 2 by c. And then what is the spatial part that I'm asking? From the principle of 4 momentum conservation, what we have learned that you can always write p mu pi. This was the pion and the rest frame decaying into two photons, p mu say nu 1 plus p mu nu 2. If I write this and I take the length of the 4 vector on each side, so what do I write? P mu, they are same particles, so I can write p mu pi equal to p mu nu 1 and p mu nu 1, same particle. Okay, maybe I could have written them together. Why I'm writing this? Maybe I should use the same notation because otherwise it may be confusing to you. Okay, let me just p mu of the photon plus p mu second photon plus twice. This time I can write separate because those are not the same. P mu nu 2, right? Nu 2. Now you see this is already known to you, m pi square c square, that's the time component square, right? There are no special component. And for the photon, চোখ বন্ধ করে লিখে দেওয়া যায় সবসময় 0 হবে, 0 plus twice this one. And what should be this, right? And suppose I write this to be p nu 1, right? P nu 1, right? And of course there is some direction associated with x component, y component and z component. What will be the, whatever be the case, you see, if you look at the center of momentum frame, or in this case particular case the lab frame here, the momentum of the 2 photons must have to be equal and opposite to each other, otherwise it will not be conserved, right? In the rest frame, the total momentum, spatial momentum is 0. So if it is suppose in the direction of n cap, of course it can have 3 component, in x cap, in y cap, in z cap. In this case, of course, we have only x and z component, there are no y components, so we can write the first and the third, omitting the second one. And if it is n cap, I'm writing in arbitrary direction. It could be anything, n cap. So this has to be minus of n cap, right? N cap, right? And remember, because the criteria is that this one has to be, so the two photon that is being created from the pion has to have opposite direction. So this will be 2 into, if I take a E nu 1 E nu 2, you can write of course, but they are going to have same frequency E nu square by c. Why I'm telling you c square, and then minus, see there is a minus sign here, there is a plus sign here, so plus minus minus, and then when you take length, take a scalar product, we have covariant and contravariant, there is another minus sign, so minus and minus becomes plus. This will be, of course you can write p nu 1 p nu 2, this will be equal, as I told you that they are equal and opposite direction, p nu square. And this will be what is, so what will be this, and you know that the photon's momentum, what is photon's momentum? P nu is E nu by c, or I can write E nu by c equal to p nu, right? So it will be twice p nu square, so twice p nu square into 2, that will be 4 p nu square, that the momentum of the photon, p nu square. So the value of the momentum of the amplitude, I should write p mu, this has to be half of, straightforward. This is not a difficult problem, but I'm going to the second part of the problem. So this is m pi c, right? So if I write p, what is p nu 2 and p nu 1? P nu 2 direction wise, if I write, this will be minus of p nu 1. Of course the amplitude is same, the direction will be opposite, because when you couple them together you get the 4 momentum of the electron, sorry, pion, which is at rest and which has no special parts, 0. It's only rest mass energy, that is the time component. Now if I go to another frame, suppose which is boosted along x direction, y direction, or z direction, or any arbitrary direction, I will just give you one example, right? You can solve it yourself, right? Once you understand one particular example, you can apply the same idea to any other problem. So I can jump to another frame, and here see, I told you the angles are theta, some angles, let's say 15 degree or 20 degree. If I go to another frame and ask the question, what will be the, say, if I ask you that find the angle between the angle of the emitted photons in the lab frame, right? So we are considering a pion system which is boosted, say, along the z direction with some velocity beta or v by c, right? So in that case, so pion is boosted, so pion is moving along z direction with velocity v. Now you are in the lab frame, so you are an observer. Earlier the pion was also in the lab frame and it was decaying into 2 photons. You were observing the 2 photons from the lab frame, and you found that the angle theta cm were equal and opposite, and you calculated that the momentum of the photon has to be m pi c by 2. But now this time the pion is boosted along z direction with velocity v. How do you calculate? How do you calculate, say, the angle of the emission of the 2 photons, right? And if you calculate it carefully, you will see that when the velocity of the Lorentz boost increases, when it tends to the speed of light, of course it is never going to be equal to the speed of light, it tends to the speed of light. As it increases 0.9 c, 0.92 c, 0.99 c, what will happen, both the photons, which in this picture you are seeing 2 photons to be coming in the opposite direction, right? In that case, both the photons will actually travel along the z direction. So if you apply a Lorentz boost along the z direction and then look at the emitted photon from the lab frame, you will find that both the photons are actually propagating in the plus z direction. So that you can show. How much time we are left with? Very little. I don't know whether I will be able to know. 2:27. Do you have a class after this? Hello?
Yes, sir.
Yes, sir.
Okay,
We have a
so-
class.
Okay. Then I cannot continue the rest of the rest part of the this problem, second part of the problem, which I will discuss in the next class. Okay, so you can also try it yourself. So what I'm saying, that you have a pion decaying into 2 photons in the rest frame or the lab frame. Now the pion is boosted along, say, z direction. Of course it can be boosted along any other direction, so I'm just giving one particular example. So take this example, that pion is boosted along the z direction with velocity v, and then calculate the angle, this, what will be the angle of emission of the two photons in the lab. If I observe from the lab frame, what should I see? Of course, if you jump to the pions frame, you will see the same event which is happening here, right? Because this is nothing but the phenomena which is occurring in the rest frame of the pion. Pion is also at rest, you are also at rest, and you are observing the decay of the pion into two photons from the lab frame itself. If you jump to the pion frame, of course you will observe the same thing. But if you observe this same disintegration of pion into photons from the lab frame, you will see something else. You will see that both the photons are traveling around the z direction. That has to be calculated and shown. So I leave this here. I will continue my discussion from the next class. Now you tell me, if I discuss by using this pen tab, is it okay, or should I go back to my previous thing that I can show you notes and then discuss? What is easier for you? I mean, it depends on your feedback. কোনটা সহজ হবে? আমি কি এভাবে পড়াবো, নাকি তোমরা যদি বলো যে আগের মতোই আমি স্লাইড দেখে দেখে পড়াবো, কোনটা সুবিধা হবে? না, সাউন্ডটা খুব ডিস্টার্ব হচ্ছে, শুনতে পাচ্ছি না। কি বলছো?
স্যার এটাই ঠিক আছে।
হ্যালো, আচ্ছা ঠিক আছে, ফাইন, তোমরা যা বলবে ঠিক আছে, ফাইন। আমি এইভাবে পড়ালো তোমাদের। হ্যাঁ বলো বলো।
স্যার এইটা ঠিক আছে স্যার, তবে একটু যদি একটু মানে আমাদের কাছে যখন নোটগুলো সার্কুলেট করবেন তখন যদি একটু লিখে লিখে দেওয়া যায় তাহলে আমাদের পরে পড়তে সুবিধা হবে।
আচ্ছা, আমি করে দেবো, চিন্তা নেই। হ্যাঁ, এই হাত লেখাটা পড়া একটু কষ্টকর, সেটা আমি নিজে বুঝতে পারছি, বিকজ মানে এখনো এটা আমার সেভাবে সড়গড় হয়নি। এটা আমাকে ইউজ করতে করতে হয়তো কন্ট্রোল আসবে। সো আই এম নট গোয়িং টু সার্কুলেট দ্য সেম নোটস হুইচ আই এম রাইটিং হিয়ার। আই উইল রাইট দেম সেপারেটলি অ্যান্ড সেন্ড ইট টু ইউ। ওকে, এনি কোয়েশ্চেন ইউ হ্যাভ? কোনো প্রশ্ন থাকলে বলো, যেটুকু আলোচনা করলাম কোনো প্রশ্ন থাকলে বলো। ওকে, কোনো প্রশ্ন না থাকলে ঠিক আছে, আমরা নেক্সট ক্লাসে আবার কন্টিনিউ করবো আলোচনা।